Tere, võtame vaikselt istet, kes võib-olla jõudnud. Et siis kõigepealt ma annan kiire sissejuhatuse eesti keeles ja siis läheme inglise keele peale üle. Et kõigepealt aitäh tulemast. Tervitan ka meie kaugvaatajaid. Et kiire kommentaar ülekande osas, et oleme teadlikud, et on olnud kergeid probleeme sellega, aga oleme aktiivselt üritanud probleemi lahendada, nii et loodame, et tänane ülekanne tuleb sujuvam, aga hoiame nappu peal. Siis osalejatele tulete meelde, et paluksime, et märgiksite oma osalemise registreerimislehel ja oleksime ka tänulikud, kui tagasiside lehe pärast täidaksite, et järgmise seminari veel paremini korraldada. Täiendõppepunktide osas, nagu tavaliselt palun pöörduda Elo Rutsepa poole, et tänase seminari puhul tessi ei ole vaja teha, kuna tegu on inglise keelega, aga täpsemad detaile jagab Elo. And for now, then I think I will transition to English. Today's topic is ventilation. Historically, at least in Estonia, up until the very end of the 20th century, most buildings were built with natural ventilation systems. And only in the 21st century is when technical and mechanical ventilation solutions are becoming more apparent. And the question of renovation is also very much current, meaning that at least in Estonia, most of these natural ventilation systems, current research in Estonia at least shows that they will need to be replaced with mechanical ventilation systems with heat exchangers. However, research in Finland has shown that alternatives are quite possible as well concerning natural ventilation, and that the building physics behind these systems might be a bit more complex than current common knowledge may present themselves. But without further ado, we have three good colleagues from Finland who have come to speak. We have Netta, Juulia, and Leino. And we will start with Netta's presentation.
Thank you.
So, please.
Hello. Can you hear me? Is my microphone working? Everybody hears me?
Yes.
Good. So, as one of the authors of the Ilmakirja, I'm now going to present quite shortly the contents of the book. This book was published in Helsinki 2 years ago, and it was very soon sold out. And another edition came out maybe 1 month ago this year, so it's again available. And this tells that, or proves that, there is a growing interest in natural ventilation or natural stack effect ventilation in Finland among just common people as an alternative to mechanical ventilation. Yes. So why we wrote this book? It's the first kind of extensive book on natural stack effect ventilation in Finland. Although this system, just like Alois mentioned, was quite common, or it was the prevalent system in building in Finland until the 1950s. And even after that, in individual buildings and terraced houses or row houses. And for example, I have lived almost all my life in a house that has natural stack effect ventilation. I'm still living in a house that was built in 1935. So, but engineers are no longer being taught in Finland how to maintain or repair or plan and design natural ventilation. And this means that we have a very high level of knowledge and know-how in how to design mechanical ventilation. But there was a kind of ardent need for a book that would show how to maintain, repair, and design natural stack effect ventilation. And Juulia and Leino have been part of teams that have been studying this in collaboration with the Ministry of Environment, etc., in earlier projects. And I came here, joined this project when we started to write this book. I'm an architect and a non-fiction writer. Juulia is an architect, designer and restoration architect who is specialized in the issues of natural ventilation. And Leino is an engineer who is specializing in energy and ventilation issues. So I think we are a very good group. So we had some basic questions that we try to answer in this book. There are some here, and one of the kind of key issues for a designer and for an engineer who is designing natural ventilation is how to prove to the authorities that it's a system that can be used in modern buildings too. So we needed graphs, we needed engineering knowledge in this project. And of course, we couldn't do this all by ourselves. We needed a network of professionals who had in the different fields of building, who commented, gave advice, or told us where we went wrong in our writing. And then of course Leino and Juulia, as they are designers, they are experienced in projects where you repair or design natural ventilation. So some basic issues about ventilation. What are the tasks? This is, well, it's the same applies to natural ventilation and mechanical ventilation. I think I don't need to go further into this issue, but to how what we deal with in this book. We have different chapters devoted or dedicated to different topics, and first of all, how does the natural ventilation operate if it's designed as it should? And this is an issue that Juulia will go deeper into in her presentation. But what is quite kind of the thing that I want to point out is that it's a passive system that doesn't need any external energy, but it works by the laws of nature. And to better understand how to maintain natural ventilation and how to improve it in existing buildings, we studied the history and evolution of the natural ventilation in Finland, and we could kind of recognize 4 different stages of it, starting from somewhere from the 18th century till today, or well, till the mid 20th century. Then there was a big gap in Finland, and very few buildings with natural ventilation were built. More about that from Juulia. Then of course we had to kind of have a look at the regulations earlier. What were the requirements for ventilation earlier in Finnish buildings? Because they have kind of directed the planning of the floor plans and of the houses, and of course of the ventilation. What is important when we start to look at a certain building that has natural ventilation, or maybe problems that should be solved, is to investigate the system in this building. And we here give some advice how to do it and what must be taken into consideration. And then again, if you want to improve a system that is not working or operating properly, what can you do? Is it some smaller measures, or do you need kind of more extensive measures? And then the question of modern architecture. If you wish to design, for example, an individual house or block of flats. How do you do it? You must start from the floor plan and in regard to the ideal placing of the flues or air ducts. So you cannot kind of just impose a natural ventilation system to any house. You must start from the floor plan, more or less. And how do you do it? Julia tells you about that. And then this is Leino's specialty, the graphs, how to dimension the airflows when designing or improving a natural ventilation system. And of course there are other ways to improve the indoor air quality, like plants inside. And for example, this is of course also an acute question. We should have more plants and trees out on the outside that give shade to buildings. And as funny as it may sound, we all need some knowledge or information about how to use natural ventilation. This is an issue that I face in my house because people don't know or understand the system, and we all often hear a criticism that, okay, it's natural ventilation, it just doesn't work, it's bad from the start. But you must know its limitations, and you must know its advantages, and then you can adjust it and you learn to live in that house. I must say that as I have always been living in a house with natural ventilation, I think it's the best. But that's my opinion. And of course, today it's quite important to take into consideration the issue of energy efficiency. And this is where Leino will give you some answers and maybe some questions, and you might have some discussion about it. But what we could say, I'm reading from paper now, sorry. Yeah, it's a proved fact anyway in Finland that old solid brick buildings consume far less energy than theoretical calculations imply. And furthermore, these buildings, for example, these buildings in Helsinki, in the Töölö region, they have been constructed in a way that is sustainable and long-lived. And so is the ventilation system, natural ventilation system. And it's generally not worth adding short-lived technology to these houses. And to end my speech, I'm showing a picture also from Töölö, which was a couple of years back. There was an article in some papers about this Adlon house built in 1939, which was called the low energy house of the 30s, because the energy consumption was much lower than those average houses in Helsinki. So they have potentials, the old buildings. Thank you. I'm giving floor to Julia now.
Thank you. So Netta already presented me. I'm Juulia Mikkola from Livadi Architects, and I work mostly as a restoration architect with small wooden houses. I've also planned some new buildings, also small. No blocks of flats, no public buildings. Is it okay if I sit? This house you've already seen. It's on the cover of the book. And I will start with the benefits of natural ventilation. The systems are simple and understandable, and they require very little maintenance. And that's, of course, also a question of money. And it's quite expensive to have professional maintenance like every year. And that's why even some bigger instances are nowadays interested in natural ventilation. Because the systems are long-lasting, they are also energy efficient, and that makes them eco-friendly. They work even if there is a power failure. That's an advantage. And they are ready for use as soon as the flues are ready, even when the building is still being constructed. So they dry out concrete structures very efficiently during the building process. And the systems need to be adjusted through vents. And some people consider that that's a problem, but mostly occupants can accept more variations in indoor conditions if they can adjust the system themselves. So this adjustability improves comfort, and for me it's not more difficult than like putting on and off electric lights to adjust the ventilation system. But of course one has to know how it works, as Netta said. And the system in itself is quiet. There is no noise from machinery, but of course the flues and the intakes, they can let some noise from outside indoors. And one of the most important things when restoring old houses is that natural ventilation systems very rarely create such negative pressure that would cause indoor problems, indoor air problems. And it is sometimes said that it's a defect that they can't have, like natural ventilation systems can't have fine filtration, but that's, on the other hand, you can say that then the microbial flora inside the house is more natural. It has many kind of microbes, and it's believed to prevent autoimmune diseases that are like getting more and more common in Finland. And for me as an architect, it's an advantage that I can tell how to design the systems. Of course, I will need, when getting building permission, I will need an engineer to sign the engineer's plans for ventilation. But I can design the house and decide how the ventilation should work, and then the engineer will help me, but he will not come and destroy my plans, which can happen with mechanical ventilation. And ventilation also has effect on indoor humidity and thermal comfort, important things considering how nice it feels in a house. And here we can see the optimum relative humidity, which should be between 40 and 60%, to have as little as possible all these kinds of problems that bacteria and viruses and fungi and mites and respiratory infections and allergies and dust and different kind of emissions from the materials could cause. And if the inside air gets too dry, then moisture starts to evaporate from skin, and then even quite warm temperatures feel colder. And then if we adjust the batteries to create more heat, the air will get even more dry, and then it will feel even more uncomfortable. So having like good relative humidity is an important issue as well. And here we have like basic different ventilation systems. Number first is often called natural ventilation. I wouldn't say that because there is actually no system at all. So this kind of buildings we can't build anymore, happily. Number two is, for me, the best kind of system. It's a natural ventilation system based on stack effect, and preferably there is a flue and an intake in every room. Number three is mechanical exhaust system, and because it doesn't have heat recovery, it can't be used anymore. And number four is like the modern thing, mechanical supply and exhaust system with heat recovery. It can create very good conditions, except that like the microbial flora in the house will be like mainly the same that humans carry with them. And it's very different indoor air than outside. And these systems, they take a lot of room. They are like space intensive, and that can be a really bad problem when renovating old buildings. Here we have the principle of the system. If air is warmed, it gets lighter and it tends to go up, while a denser, colder air tends to go down. So if we have an indoor space that has heating, and then we make a flue up to the roof and an intake, a hole in the wall, then the air starts to move. And we can see the different airflows. There is the outdoor air coming in, warmer indoor air, and then supply air, also called replacement air or intake air or fresh air. And then if not every room has an intake and an outtake flue, then there is also transfer air that is flowing from one room to the other. And then of course exhaust air going up through the flue. And when designing a house with natural ventilation, there are certain things one should remember. The flues should be sufficiently spacious and high enough, and preferably vertical. And that's why a flat roof is not so good. A pitched roof is a lot better, and an attic is also an advantage. And here we also see a traditional way of arranging the flues in a multi-story building. And doing like this, you can have the same floor plan in every floor. And one important thing is the height of the flue, but actually when you are calculating the ventilation rate, you are calculating the height from the intake to the top of the stack. And on the upper row you see different examples. Like even if you have the same height in the flue, if there is a different height in the intake, it affects the system. And in the lower row you can see the normal situation that because upper floors have shorter flues, the ventilation rate is lower. And in the ground floor, the flues are very long, so the ventilation rate is quite high. And this is sometimes thought as a bad defect, but it can be avoided by taking air in near the ground floor and then using intake flues. And of course, natural ventilation rates differ depending on the season and on the weather. Wind boosts natural ventilation a lot, and it also helps with different airflows in multi-story buildings because the effect is stronger in upper floors and doesn't affect that much the ground floors. And in wintertime, when there is a greater thermal difference, the ventilation rates are a lot higher than in the summer, and that's one reason why we need to have these adjustable vents. And natural ventilation always needs operable windows to help during summer and actually before summer, because ventilation is also used to remove heat from buildings. And that happens already when the daily average temperature is around 10 degrees centigrade. And in Finland, the year-round average temperature is like 5 degrees centigrade. And in July, it's like 17. And mostly during summer, inside temperature is about 4 degrees higher than outside. So there is normally always some kind of thermal difference. Of course, there are moments when it's really hot outside, and if you have a massive house, like massive structures, then in the afternoon it can be cooler inside the house. But then also the stacks, the chimneys are probably like warmer because sun has been shining on them. And usually it's always a bit windy. So the system works quite well even if it's warm. Window ventilation can be used through one facade, and the best thing is if you have a chance to have cross ventilation through the house, or then ventilate between different floors. And on the right we see different kinds of ventilation windows, sort of old-fashioned health window that is being used again. And then ventilation pane called fortuska in Finland. I don't know if you have the same thing here. Traditionally, the inner panes were taken out for summer, and then for winter they were sealed by gluing paper on the gaps between panes and frames. And then it was really practical to have this fortuska so that it was still possible to ventilate through window. Sometimes it's said that because there can be down draughts in natural ventilation, it would be better to adjust mechanical fans. But this down draught, it has a reason. It's, if there are many flues but there is no intake air, then the one flue that doesn't work as effectively as the others, there is a reverse flow of air. And giving the system more replacement air usually corrects the situation. It's also possible to have a room like inside the building, like a small toilet. And if it's cooler than the rest of the rooms, it's possible that air starts flowing in through the flue. And better than adding a machine is to add a wind cowl, and here we can see traditional revolving wind cowl. In Finland, this kind of thing is called Jonnin imuhattu, or jonne, or jonnari. It's a, how do you say? It turns with the wind, it doesn't really spin. And you can add it just on one flue of the apartment. It's not too strong, like to change the airflows in other flues. And mechanical exhaust has also this problem that because it causes a strong negative pressure, it's possible that if there is not enough replacement air, it starts sucking unhealthy stuff like from the floor, from the ground, or from the wall structures if they are old and have, for instance, mold. Here we can see the parts of natural ventilation system. The core is the flue, the most important thing. And that's also the thing that has to be thought of when designing a floor plan for a naturally ventilated house. And there has to be an exhaust vent that should be adjustable, and then an intake that needs some kind of shelter from weather, from rain, a grill, and then the adjustable intake vent. And there needs to be the operable window. And then one very important part is the occupant who knows how the system works and who adjusts the vents and the windows. And if it's an overflow system, then we also need these transfer air gaps, like door gaps or vents. And then there is this wind cowl, not necessary in every house, but very, very useful in many cases. And the best possible flues, to my mind, are made of red brick, but also concrete and precast blocks can be used. And of course, metal sheet. I'm not so fond of metal sheet because it can have convection problems and it doesn't store heat. So it doesn't have the good effect during summer that the chimney gets warmer and enhances the flow of air. Netta was already talking about this evolution of natural ventilation systems. Here we can see the fireplace heating and unintentional intake. This was common even in multi-story houses in 1880s. And on the facade you can see that on the uppermost floor there are intake holes, but the uppermost floor was made in the 20s. And the lower parts, they have no intakes, because at that time windows were not that airtight. And as the heating was done with fireplaces, the fireplaces or the chimneys, they caused stronger negative pressure that did suck air through the windows. And of course, the windows were operable. And the second one is my favorite, room-by-room system, or a room-specific system, where every room has a flue and an intake. That was ordinary from the end of the 19th century till the 30s. And with the modern times, there were improvements with overflow method that was used till the 50s or 60s, and it's still used. It can be quite good, but because there are less flues, it's not as efficient during warm seasons. And then the last one is the sad part, like saving more and more in the expenses of the flues and the vents. The latest system of these in the 60s was just having exhaust flues without any replacement air, or just unintentional replacement air and ventilation through windows. And because of this system used in the 60s, the ordinary opinion was that natural ventilation doesn't really work. And here you can see on the facade that there are only few holes, and they are the holes of wood storages. They are not really intakes, maybe for the room. A floor plan of the first phase. Here you can see that every room has a fireplace. The kitchen has two flues because there is the cooker hood, and then the fire flue for the cooker. And then there are masonry stoves for heating in every room, and ventilation was possible through the fireplaces. There are no vents on the facades, and there are no door gaps because the doors weren't considered to be a problem at the time. A room-by-room system, this kind of house could also have fireplaces, but this example is an early central heating house. And here you can see that there are intakes in every room, and some of the intakes are serving 2 rooms actually. And there are food storages that can have 1, or as here, they can have 2 holes on the facade. At the food storage, the facade is a bit thinner, and because of the vents, the food can be kept cool during winter time. A modernistic house, less flues, and most of the intakes are connected to the windows. They are slotted vents, not this kind of rectangular holes in the wall. And here we can see the overflow system where there are door gaps, and this kind of system was considered very efficient because the exhaust air from one room could be used again as fresh air for another room. But actually, as I said, during summer it was sort of it was not efficient enough. And the last system, not a good system anymore. It's like only half of the system, because there are flues, but there are not like proper intakes. It's just unintentional intake air through the windows. Here we can see different kinds of exhaust vents. At the early stages, the masonry stoves didn't have exhaust vents, and then the ventilation through the fireplace was done so that the doors of the firebox were kept open, and diverting, how do you call it, pelti, säätöpelti in a storage. Well, you know the things that you're pulling and pushing to make a fire. Well, if you keep those open and then open the doors of the firebox, then air starts flowing through the fireplace. But the firebox might not look so nice, so screens were used to hide the ugly firebox. But soon, as there was this problem that if you ventilate through the whole stove during heating period, then of course the stove gets colder, so you lose energy. So it's more efficient if you have an exhaust vent on top of the stove, and then you can open it, and if you have double pelti, then you can open the upper one and the air can flow and only cool the upper part of the stove. You can see a cooker hood and a few examples of old exhaust vents, and then ways to prevent downdraft in brick chimneys or flues. It's good to have like a deeper part behind the vent, so that if there is a downdraft and the air starts flowing down the vent, it doesn't like pour straight to the inside, but it turns around towards the flue, and this hole on the bottom, it also collects like rainwater and pieces of the seams when the chimney gets old, and dry leaves or other kinds of rubbish that can come down from the chimney. Here you can see how air was taken in through inlets. Depending on the thickness of the wall, different methods were used, and thick brick walls were good. You could have a Z-shaped intake, actually not just the hole, but the short intake flue. And that would prevent rainwater and dust and light and wind getting straight in. And in the turn of the 19th and 20th century, the flues were done so that there was a vertical part, and in the 50s they were done so that there was a horizontal part, so the Z was horizontal. In wooden buildings where there is not enough depth on the facade, the oldest systems were this kind of L-shaped pipes that had like a separate lid on the inside. And then with industrial products, there were flap vents. In the first phase, they needed to have something where to a thing to hold the thread with, but later on they became like self-closing. And then we can see this disc plate or disc vent that has the disadvantage that air can flow like down, and it causes more draught like on the floors. It's not as convenient as air going up towards the ceiling where it is mixed with warmer inside air. And then to the modern times, or to the 30s, where slotted vents were used a lot. Here you can see from the drawings that in theory, very nicely the heat from the radiators, it mixes with the incoming fresh air, but actually what happens in these kind of systems mostly is that there is like when it's windy, a very cold air shower like coming straight towards people. So these are not even sold anymore, this kind of vents, because they were not really comfortable. And on the right we have can see a very special system. It's from a schoolhouse from the 50s where air was taking in between the panes, so there was a gap on the upper part of the outer pane, and cold air got in between the panes and then poured down, and in the inner pane there was a glass hatch that could be adjusted. But this is a special case, not a normal thing in Finland. And because these were so commonly used, we had a lot of Finnish industry making these kind of things, as we can see here from National Library of Finland. And then some new examples. Natural ventilation was unintentionally banned in the energy regulations in 2012. But 2018, the regulations were improved, and now it's possible again. And this house was built as regarding to the energy regulations as a small exception. It didn't, like the calculations show that it's not actually good enough, but the architect in the building permission office was thinking that because this has massive structures and natural ventilation, and actually we know that it's better than what the calculations say, she thought that it's okay. And this has sort of an overflow method. It doesn't have an attic, so that's why it has spinning wind cowls that are quite efficient on the chimneys or the stacks. And this is a very new example and very encouraging one. It's a multi-story residential building, massive brick facades and natural ventilation. It has different kinds of intakes. On the other side, there are holes and grills on the facade. On the other side, where the balconies are, the intakes are made so that there are intake flues between the walls between the apartments. So there is an intake flue where the air gets warmer, and then the different floors have the same ventilation rate if we are not considering the wind. And one of my examples, like for me, this is a really big house, but it has 4 apartments, and it has been erected on an old railway station area, and it tries to adjust to the old buildings. It has massive wood facades, it has brick chimneys, natural ventilation, and here you can see an L-shaped intake that we designed. These were not really made in the house because they were like the developer had so many problems, like other problems, that she decided to leave them out. Here we can see the floor plans. It's quite systematic and simple, and how the flues are in the firewalls between the houses. And some photos. Here the structure of the outer walls is so-called WLT, like wave laminated timber. And here the manufacturer went bankrupt, so the developer who had bought these facade elements lost them because they were not transported to the site when the bankruptcy occurred, so she had to buy them again after the bankruptcy. And she actually hired people from the company so that she could complete these elements. So that's why she didn't follow all the details of the architecture plans. And here some places where you can get more information. Of course, our book, but it's only in Finnish and you have to buy it. But then the Ministry of the Environment has an document. Leino and I have been working with it, as we have been working with heritage agencies. Now I'm losing all the words. Käyttäjänhuolto, like
maintenance.
Maintenance, yeah. And the Swedes have made a really good document, also available in English, and it has many examples about how to react when you have an old building, an old listed building, and what kind of possibilities there are. That's it for me. Now I'm asking for Leino to come and tell us about energy things.
I would like to ask, do we have any questions at the moment? Okay.
If you just add with some words in the site of Muurimester about the massive walls, or will Leino talk about it?
Will you?
No.
So what would you like to know?
Just the idea of the massive, very thick.
Go back to the picture.
Yes. No. Here. So this house has like massive brick walls, but actually the structure inside is made of concrete. There are pillars and slabs like holding the house together. For me it's sort of a normal thing, but we are like quite an exceptional office. I've never designed, well, I have designed one building that has mechanical ventilation. That was a small cafeteria of 40 square meters and having maybe 30 people, so it was impossible to have natural ventilation. It wouldn't have been convenient enough in the winter time. But what more do you want to hear about the structure?
What is the thickness of the massive brick walls?
I think it's 60 centimeters. And this house was actually also, it had a small exception in the permission. Up again with the energy performance, there is in the regulations there is a lower U value for massive wood structures. But in Helsinki area, the officials are already thinking that it applies also to massive brick structures. So in this building they have used this. Did you, Leino, work with this muurarimestari? Did you do the calculations?
I was doing some energy calculations.
And they were using this like small exception in the regulations that because it's massive you can use the lower U value.
Yeah, they were able to get that for this house, even though it's not logged. Because usually it's only for logged buildings.
So that shows that in Finland, like somehow the atmosphere towards natural ventilation has changed for the better. So it's possible, it can be done.
You can maybe explain the third picture there also. It's a strange picture, I think.
Yeah, that's where the on the other facade there are like intake flues, and the air is flowing up to the apartments from the arcade of like here you can see on the other side that there is an arcade under the balconies, and on the ceiling of the arcade there are these holes where the air the flue start there.
Okay, then thank you again, Julia.
Thank you.
And we'll continue with Leino.
Mun pitää antaa tää karvahomma.
Yes, thank you for the invitation from my side.
Invitation?
Yeah, let's put that first. I gather it wasn't open here, so.
It was closed. Yes, it should be on the desktop. And then the three dots.
Yes. Okay, that one works. Yeah, so it's my first time speaking in English about this subject, so bear with me. I think I'll also sit here and have my notes on the side, just in case. So about my background, I have studied in Aalto University in Otaniemi, Espoo, and done my master's degree in energy and HVAC technology there, and basically I have worked all my career in building design, doing the energy calculations and then doing mechanical ventilation design. And yeah, so this is an interesting chance to visit Estonia and also get some experience on the systems on this side of the sea, because this yeah, and if you don't hear me or if you have some questions, just please raise your hand or shout. Yeah, so like the natural stack ventilation, it is kind of like it's not a Finnish method, but it's the Nordic countries. So Sweden has it quite a bit. Denmark has it slightly, but it kind of disappears when you go more south than that. So it's about about the environmental conditions that allow for this kind of ventilation system. So it's not a very global thing, and I think that's also, the book is in Finnish, so let's see if we get some translations at some point, maybe. And then, so now I'm gonna give a bit of a deeper dive into the regulations side of things and the energy things concerning ventilation and natural stack ventilation. And then when I talk about mechanical ventilation, then it would be the intake and exhaust type of mechanical ventilation, so the modern type. And then the natural ventilation is natural stack ventilation. And so here a bit more about the advantages and disadvantages for this type of system. So we have the system is dependent on the weather conditions. So we have to have the temperature difference, and also wind is helping the system to work. But this will cause that it is fluctuating, the working power, the pressure differences are fluctuating, and that means that the user has to adjust the system. But of course that can be also be seen as a benefit, because it has been shown in some studies that when people have the possibility to adjust temperature, for example, they have a knob on the wall that they can adjust, then they also feel more content with the environment, even though the knob would not be connected to anything, and then just have a knob on the wall that they can turn and feel that they have a power. But anyway, in the natural ventilation system, you are actually in power, and you can adjust room by room. You can adjust the airflows, and if you feel that there is too little air, then you just open a vent or open the window in the summertime. Then there's less moving parts, so it's a simple system. There is less noise pollution from the system. The pressure levels are lower in the natural ventilation system. So if we have a mechanical ventilation system, we are talking about 100, 200, even more in bigger systems of pressure in Pascal. In the natural ventilation systems, it's in the summertime it is 1 to 2 Pascal. In the winter time it's 10 to 20. That's about the range. So the pressure levels are very low, so you have to design it, the design has to be precise in a way that you have enough flues and enough vents for the natural ventilation system. You can't just turn the fan power higher. That's not an option. And then there's no risk of air contamination, that if the adjustments are done wrong, if somebody closes all the intake air vents, for example, which can happen in certain types of situations. In older, like mechanically ventilated houses where you have only the exhaust, ventilation is as mechanical. But in natural ventilation, even if you close all the vents, you will not be able to suck impurities from the structures, through the structures. So the low pressure is a benefit, but also it makes the design more difficult. So all of these, they have like two sides to them. So it's more like it is a bit of a philosophy question on like where do you want to go with the system choice. So are you kind of more technology dependent? Are you more low tech? Also, natural ventilation doesn't need electricity to work. It generally needs less maintenance, and it has a longer life cycle. Then, like doing a really efficient mechanical ventilation, you can get a better, more precise air quality. You can get higher energy efficiency if you do it right. Yes, okay, maybe that's about this subject. This is the definition of natural ventilation concerning the building regulations in Finland. So this is the natural stack ventilation, so it's height difference and partly also wind driven, but mostly it is the height and temperature difference that we are dealing with. Yeah, so we had a new building regulations which came 2018. They came into force, and in that round of changing the regulations, they kind of took natural stack ventilation again into the regulations as an option. So it was actually mentioned before this. The regulations was basically just for mechanical ventilation. It was not really mentioned there, and not really regarded as an option. And then also the energy regulations, they were becoming, every time they were updated, they were becoming more tight. So at some point for natural ventilation, the situation became that it was still possible in theory, but in practice, basically all of the designers had already decided that it's not worth it because there is so much balancing that you have to do on other like other design choices that you have to kind of tighten, or like make thicker walls, have better windows. All kind of more expensive stuff that you have to do if you want to have the natural ventilation system. And then also the building inspections, they pretty much were against natural ventilation because the energy efficiency subject was so much on paper then that it was regarded a bit like heresy to suggest this kind of natural ventilation, which wouldn't have the possibility for heat recovery. But then this was pretty much a political decision that they then took it again as an option and also actually gave an exception from parts of the energy regulations. So here it's the fulfilling the heat losses limit, vertailulämpöhäviön laskenta. It's an Excel spreadsheet that the energy expert has to calculate, and then in there the ventilation heat recovery is taken into account. But nowadays for natural ventilation the requirement for heat recovery is 0%, whereas for mechanical it's 55%. So that's a big difference. Even though for the energy certificate we still have the same limit. So basically the houses with natural ventilation, they can't use any more energy than the houses with mechanical ventilation, but you have to use other means. But this one calculation was many times like it was a big issue, even though it doesn't it's not the full picture about the energy efficiency even. Yeah, so for new buildings the situation is nowadays much better, and also the treatment from the building inspections, it has changed in the last 5 years. I have been working quite intensely with natural stack ventilation from about 2016, and during that time how it's regarded in the building inspection offices, it has changed quite drastically. So nowadays they do take it like the designers. Many times the designer still has to show like in calculations a bit more than would be required for a mechanical ventilation, but it is not like from the beginning that they will say no to the option. And then, well, as we are in Maa-arkkitehtuurikeskus, in the municipalities that are more on the countryside, these things are much more simpler. So nowadays, when the kind of like the mentality has shifted, so in a municipality on the countryside nowadays there is no problem, and even the plans can be about the same quality as for mechanical ventilation, natural ventilation, mechanical ventilation. They are treated the same. So if you have a good-looking plan and you have the flues there in the right places, that's okay. You don't have to even show any calculations. In the cities, it's more difficult still for natural ventilation. But on the countryside, the situation is already very good. And then regarding renovations, there has been also some issues that in some cases building inspections have because of the energy regulations for renovations, they have even sometimes decided that you have to update your whole ventilation system. That was pretty much like in the beginning when the new regulations came in force, but then that hasn't been the intention from the Ministry of Environment to begin with these regulations, and they have many times now said and corrected that if you are maintaining or repairing this natural ventilation system, it is not a requirement to put in heat recovery. So you can basically indefinitely you can upkeep your ventilation system in the form that it is, which is of course quite good. Yeah, there it is in writing. And then we have some studies have been made about like follow-up studies on existing buildings in Finland. So I will tell a bit about these results and talk a bit more in depth about this energy efficiency issues. So this is one big study that has followed up about 100 single-family homes, and they were measuring. This is from Tampere University, or is it? Yeah, Tampere Technical University. And they were measuring many things from these houses. They were all of the houses were already in use, so the residences were using them as normal. They went there and measured, for example, the air exchange rates in these buildings. In the winter time, they did these measurements, and they didn't make any changes. So if the ventilation was low, it was low. They didn't make any changes to the habits of the inhabitants. And it turns out that the ventilation rates that they used in naturally ventilated houses were 25% lower in the winter time than the ones for mechanical ventilation. And yeah, this was a study where there is no they didn't find a correlation that naturally ventilated houses would be higher consuming than the mechanical ventilation houses, and there was no strong correlation with the type of ventilation system and the energy consumption. But there's of course a lot of factors that play into this. The ventilation energy consumption is only about 20% of the whole. So, and then the study conclusion was that the living habits of the inhabitants is definitely the highest influencer in the results of the energy use of the houses. But the lower air exchange rates are partly due to the natural regulation of ventilation rates in these types of systems. So when you take the air through the vents directly into the room, and it comes at the temperature that is outside. So if there is cold air coming in, then people will notice cold draft when the airflows are large, and they will usually then go and close the vents at least slightly, so that there's less air coming in. And in the Finnish climate, this will lead to even better air quality. Because of this, the humidity factor that Julia was already referring to before. So, of course, it's not good if people go and completely close the air vents, but if people know the system and know how to use it, they will not do that. They will just slightly close them and adjust it according to the weather outside.
Sorry, quick question. In the study, was indoor climate quality assessed or measured in a way as well? Or will we speak about it? Or did it just concern the energy consumption? In terms of, yes, in winter there was a lower air rate, so people would close the air vents more, but would that cause some people to feel that, okay, I'm doing this because of the draft, and maybe they felt that the air quality would have lowered from that? Or was this an aspect in that study too? Or was it only energy consumption?
Yeah, I do think it is quite an extensive study. And yeah, I don't think that this has a very big effect on the air exchange rates. Still in those houses, they are quite close to the levels that the regulation also requires. So it's not a drastic decrease in air exchange. But now I don't remember directly, like, if the people were asked about the feeling of air quality. So that's. But you can also go through the study and check, because there is quite a lot of data, and they have really measured many things about the houses. So it's a very interesting study to go through for like a practical, actually like houses that are lived in and in practice.
I have a question. The energy consumption is about this ventilation mechanism, or is it also the heating system included there? Like if you have the open vents, you get the cold air in, and then you want to heat the room, then the temperatures go down, you have to put on more heat.
Yes.
Is this also included in that study? Like
yes, they have in this in the study. They took the total energy consumptions and they were comparing those.
Okay.
So it is actually including all the energy consumption. So the heating system, also energy consumption of the electricity consumption of the fans, but also of the appliances. Like everything is there.
Okay.
And it's not really separated out either, so it is like clumped in. So energy consumption is energy consumption, and it's like what is the effect of the ventilation specifically. You can't really make it out from the study, but it shows that these houses that do have the natural ventilation, they are not, at least they're not kind of standing out from the data, that they would be worse than the general houses.
I was reading an article about this research when it was being done, and at that time they were saying that the naturally ventilated houses had smaller energy consumptions than the mechanically ventilated houses, and when comparing the mechanically ventilated houses, heat recovery made no difference. So of course they were expecting that in the houses with heat recovery, the energy consumptions would be lowest, but it wasn't at that time. But of course the research is somewhat old, from 2005, and heat recovery units have gotten a lot better, so we would need new studies.
Yeah, but also the problem with the data is that they haven't looked at same kind of houses. So the houses are all types of houses basically. So if you take a natural ventilation house and you take a mechanical ventilation house, they will not be identical houses. So basically you can't like make a specific conclusion, but in general that was the houses with natural ventilation were actually quite energy efficient, but there's many other factors that play into that data. So, but at least we can say that they were not like consume. They were not the higher consumers, the naturally ventilated houses. So it's not a big factor in the energy consumption there. And so continuing on this, why I say that the air quality might be even better with smaller airflows. That's kind of counterintuitive, but this is talking about the Finnish climate in the winter time, and the comfort also relating to relative humidity in the indoor air. And basically when it gets colder outside, the outside air is drier, and when you take it in and heat it up, it gets the moisture stays the same, but with the heating, the relative humidity goes down. So in these we can see that the lower levels of ventilation rate actually give a climate which is more comfortable for people. So the perceived temperature comfort is better here with 4 liters per person than at the really high 12 liters per person. So that's one impact of the ventilation. When we talk about energy efficiency, it's winter time is the time that we talk about. So actually taking down the ventilation rates in the winter time makes a lot of sense for well-being of people and for energy efficiency. And then when we do that, the effect, the gain that we can get with the heat recovery ventilation becomes smaller. So this is one factor that is kind of in favor of using natural ventilation also. And then there's another study done in Finland about performance of people in office environments, and how there was also a lot of stuff in that study, but they were also studying the effect of air or ventilation rates. And the conclusion was that having very low or very high air exchange rates was not having a big impact on the performance or the comfort, perceived comfort of the people working at that office. But the important factor was that they had a cooling and heating system for the office, and they were able to manage the temperature in the space. So even with the low ventilation rates, the temperature were not allowed to rise. The temperature was the same for both of these cases. And then they were looking for general comfort of people and how they were doing in some tasks that they were given, and then they were comparing these ventilation rate cases. And actually, I think there is now there is a discussion about these ventilation rates. Now in Finland we have like 6 liters per person is the norm that is in building regulations that you have to have. and then but there's talk about lowering these rates now. I think in like the Europe REHVA, I think it's called, the European HVAC Association, and at that level they are considering if they should actually take down these recommended rates for people. Let's see what happens with that. But in the winter time, like if we don't talk about regulations, we talk about general use of residential houses, then like taking down the airflow slightly in the winter time is generally a good idea in the cold climates. Yeah, now from all of this, like we're slowly getting to the main point, and the point is that in the energy certificate calculations that we do in Finland for houses, these practical considerations like taking airflows down in the winter time, they are not taken into account. The airflows are always taken as constant all year round, and at the higher level, even a bit higher than would be like nowadays the requirement of the building regulations. And then there's some other factors, like in natural ventilation we have the easy possibility of taking down the air exchange rates in those rooms which are not in use. So if there's like an extra bedroom in the house, you can actually have the vents really small in that space without affecting the house otherwise. In the mechanical ventilation case, that's normally not possible at all. You just have one speed adjustment for the machine, and then it will affect like all the spaces in the house. So this kind of adjustment possibility is helping with the energy efficiency also. Yeah, and in practice, how these things will affect the energy efficiency. This is like an output from calculations that I've done using the same method that is used for the energy certificates. And this is only taking into account the heating requirements for the ventilation air, and also the electricity consumption of the fans of the ventilation machine. And on the right side here is the case with the calculation parameters that would be used for normal energy certificate. And there we can see that like all these green spots, so from heat recovery efficiency from 85 to 55%, and then the electricity consumption of the fans. So there is like these red ones are the minimum requirement of the regulations, and then we can go better, of course, with both. So counting this way, it shows that the mechanical ventilation with heat recovery is better. It is more energy efficient. But if we take into account that the airflows in the natural ventilation system will be actually adjusted with the with the weather, with the season. Then the result looks quite different. So in this case, like a average mechanical ventilation system would consume about the same if you count the electricity consumption and the heat consumption. And then we can go like with a passive house design, so we do a very high efficiency for both the electricity use and the heat recovery efficiency. Then we can go better than the natural ventilation, but we can also do like a cheap house with just barely fulfilling the regulations, and then we're actually doing worse than for the natural ventilation case. And one important part of this calculations is that we assume that we are using like a modern heating system with quite an efficient ground source heat pump, which is nowadays pretty much becoming the norm in Finland for new build single family homes. So taking into account that factor and the like the practical use of these ventilation systems, then like doing a natural ventilation system is not really a crime, considering like this energy efficiency side of things. Yeah, how are we doing on time? Are people ready for a coffee break? Or
Just about. Are you about to finish? Or?
Yeah, like I have some pictures of like some system parts here that I could go through, but maybe I can go through them quickly. It won't take a lot of time. Yeah, so some like flue possibilities, some flue structures. So this is the old style with brick. And then we have from Schiedel, nowadays we have this light concrete precast like element flues. They are actually designed for natural ventilation specifically. They have the ones for fireplaces, but they also have a product for natural ventilation. This is this is their use in practice in a renovation. And here is another case with that product. And then there's also some other types of these ones. This is basically the same brick material, but in a different form factor. I have had one project where this product was used, but it's not. This is not even usually available in Finland, but Wienerberger ordered it from Denmark, or I don't remember exactly. They were able to get it. Yeah, and then some modern products for vents, which are taken from the old style and redesigned. Also with better insulation. And then this is like completely the old style, but just as a new product. And then there's some like which are these are products that some of these are for mechanical also. So this is like a intake air fan, which is not actually taking air in so much as to recirculating air. So room air is recirculated to heat the incoming cold air. So you get better conditions in the room without cold draft, even if you take cold air in through the walls. And then this product is nowadays very popular in Finland. So it has a thermostat. So when it's cold, the vent will close automatically to a smaller opening, and then it will open when it's warm. So in natural ventilation, it's very good because people don't have to adjust the ventilation so much. It kind of does it automatically. And it's still quite low tech. There is no electricity, just a regular thermostat. And then these are just very simple, like vents for natural ventilation, for the exhaust. And then, so there's the jonnehattu, jonnari style, and there's the rotor style of wind cowls. Yes. Yeah. And then just a small mention of Domus Classic that is selling also these products because they helped us to get the second round of publications. What's that? Second edition of the book out. They actually took the risk and decided that it's worth selling. So. But also, if you need these products and you can't find in Estonia, maybe that's a place where you can look. Yeah, now I think time for coffee, if there's no questions.
So as after we will be having a break now, let's take 30 minutes, so we continue at 14:15. If you have any questions for our Finnish friends, then Netta will be having another presentation after the break. So if you have any questions, I'm sure you can use your opportunity then or during the break. And then as the final presentation, we will be having Ülar Palmiste from Tallinn University of Technology to introduce the Estonian perspective to this question of ventilation and renovation. But let's have a break and let's meet at 14:15. Thank you. But please.
I will be following the example of my colleagues and sit down. So we were also asked to present a few cases where you have a protected or listed building and there are issues with ventilation. So we chose basically 3 examples from different centuries. The Lohisaari Manor in the left from the mid-17th century. It's a museum today. And then the former main building of Alikartano from the end of the 18th century, and then it's a museum today. And then a residential and commercial building from the town of Tammisaari that was finished in 1880, the Lydvan House. This one. Yes. So, is anybody familiar with Lohisaari? All right, a few words about it, what it is about. It is known as the home of the Fleming family, which was an aristocratic family in Finland, and then of the Mannerheim families. So the Corps de Logis, or the main building, which can be seen in this picture, it was built by the Amiral and Governor-General of Finland, Herman Fleming, in the mid-17th century as his residence. And it needed to be really prestigious. It's one of the few masonry manor buildings that we have from that era in Finland. Mainly all the manor houses were built of timber at that time. So this was really something exceptional. And several of the Lohisaari Flemings, they held important positions in the Kingdom of Sweden, Finland. So they also had posts in Stockholm. And then the Marshal of Finland, Carl Gustav Emil Mannerheim, was born here in 1867. I think everybody knows Mannerheim. Yes. And spent his childhood here. And then in the early 1960s, when Mannerheim was already deceased, there was a committee for an equestrian monument. That meaning Mannerheim riding a horse. This committee for the monument for Mannerheim bought the main building, or the Lohisaari Manor, and donated it to the Finnish state. And it was then, the administration was, or the museum in charge was at that time the National Museum of Finland. And nowadays it's the state-owned company, Senate Properties, that is the owner of this building and also supervises its restoration and use. And Livadi Architects has been responsible for the restoration design, including everything from conservation of surfaces to ventilation and plumbing. And we are also making a building historical survey of the building at the same time, both to help the restoration process and also just to document the history of the building of Lohisaari. And actually the same applies to all these examples that I'm here showing. They are projects from Livadi, and here the responsible architect is Marko Huttunen, who is Julia's husband, and the other projects, there the restoration architect is Juulia. Okay, and the only kind of modern time commodity or amenity that it has today is electricity, and it only has it in some places. So it's really kind of, in a way, very authentic today from the surface. the building. So there are of course many different issues as for the use and the comfort of the clients and guides in the museum, as it was opened as a museum in the 60s and then underwent a rather comprehensive restoration where also old structures were dismantled because they wanted to kind of have the more historical look for the building and especially for the interiors. But one of the big problems nowadays, and probably growing with the climate change or getting worse along with the climate change, is the heat load in the building, because it has no kind of ventilation system, actually, this building. None, I think no manor house of that time would have had it. And this is one thing, and another thing is that it's a museum with museum objects and furniture, textiles, paintings, etc., and there is the UV radiation that should be kind of shut off. And earlier, against the UV radiation, they had roller blinds, but this has proved to be an insufficient way of shielding the interiors, and also it blocks the views from the inside to the outside landscape, which is actually quite important for the good experience, museum experience. So now with consultation with Leino, Livadi has designed two main measures to kind of cope with this, the heat and UV radiation problems. And I like to anyway show here. You see that the heat load is naturally kind of biggest on the southwest and southeast sides. And the idea is that on this side, the windows shall have both a thermal shield or a shield against temperatures, high temperatures, and a UV radiation shield. And on the other sides, facing more or less north, only UV radiation shielding is needed. This is ongoing, so we don't still yet have any results of these measures. And then another thing here is that we are utilizing the stack effect. This is a rather tall building with a very tall attic, open attic, actually quite historical, and a dark roof. Today it's black. It's a wooden roof, but it's painted black. So it will get rather hot in the summer, and also this attic space will be rather warm. So this will then create a stack effect when we have certain arrangements on the interior. So the idea is to have night ventilation. The building will be ventilated in the night time. After the museum closes in the evening, the guides there take some measures. They open this window here, which will be specially designed to be used as a ventilation window, and also a burglar-proof and bird-proof and insect-proof window. And then doors are opened to those spaces that need ventilation or cooling, so you can select which rooms need it. Not so many rooms need it actually here on the first floor, but then with the stack effect, the cool air is going upstairs. I forget about this. Yes, here you see the ventilation window that will be replaced don't worry, this is not an authentic window. It was done in the 1960s, so it's not from the mid 17th century. It will be replaced with this kind of a window in the summertime, which has a copper grill that and an insect net or a mesh, so you won't get insects, birds, or any rubbish from the outside. However, you might get some wind inside, but this also kind of slows down the force of the speed of the wind. So there shouldn't be any problems really with some rainwater. And during daytime, there will be wooden shutters, so that the kind of the user experience will be different. You just think that, okay, this kind of shutters, you could have this kind of shutters in the old days too. So this is only for the night time. But also it's adjustable. If the weather forecast says that, okay, there will be really hard winds in the night, then you maybe don't open this at all. And then the idea is that because of the stack effect, the cool air circulates higher up and ends up here on the attic. There is a stair, and it's an open stair from the first floor. There are no windows, no walls, and no other obstacles. And here they will install a door with similar arrangements. It has a mesh in order to prevent insects, etc., but it's breathing in a way. And then on top you will have two skylights, original skylights, where the windows will be replaced again with this shutter with copper grills, and it will be opened for the night. That was that. Any questions? All right. So the second case is this museum in Mäntsälä, some 65 kilometers from Helsinki. And this is the actual main building from the early 19th century, and this is the former main building from the late 18th century, the Alipytinki. And Julia has been responsible for the restoration design of this museum for some years, and she actually might know the history much better than I do, but you correct me if I make any mistakes. So this manor became also state property in the 60s, and it was then converted to a museum, and is managed by the Senate Properties again. And it has some ventilation issues here. This was converted to a cafe in the 60s, but before that, some history. Here are some kind of measure drawings from the 60s, where you see the kind of layout of the 20th century when it had been converted to residential use for some, well, farm workers, I guess. And when it was converted to museum use or to a cafe, they built new chimneys. And the chimneys were different than the original chimneys, which you can see here, in a way, that the original chimneys had 3 flues. But when they were now converted, the top part of them only 1.5 flues, and here one flue was in use or left open. Was it right? Yes. And now in this restoration, where you see before and after, so this is today, they made some extensive work with the frame, which also involved making it a little bit more airtight, the frame, with this birch bark cladding under the actual cladding. But what was also renewed, or will be renewed, are the chimneys. But I will go into that a little bit later. So the problem in the cafe was very much the same as in Louhisaari, that there is the problem of overheating in the summer. And another problem is that the ventilation was quite poor for the clients and for the workers there. And then Julia started designing solutions to improve the situation. And the main measures were adding vents, like here see vents with a rain cover on the exterior or on the facades. They're quite kind of not very kind of striking, and you see a lot of this kind of vents in historical buildings in Finland. And that's what it looks in the inside. You have those rather expensive vents, but I think that they quite well work with this historical environment. And then as exhaust air vents, Julia designed to use both those vents in the ovens, like you see here, and then there are some other places too where they have added or then just kind of repaired the vents. And this is only in summer use, so it doesn't work. The cafe is not in use in the winter time. And here is the kitchen. I don't really know, do they prepare food there really, or is it just something that is prepared?
This is the kitchen for the staff. This is the staff room. And so they just make coffee and warm up their lunch there.
Yeah, so no heat load from there.
No.
And this is from the cleaning closet, where what you cannot unfortunately see here, you designed a wooden kind of duct here, which could have been, in a way, been designed in any earlier century as well. I think it's a very nice idea. And what is not yet finished, but will be done this year, is the improvement of the chimneys and the flues. They will be opened. This is how it is now. Will be opened so that they will work better, kind of suck better air from the inside. But even already now, before the improvement of the chimneys, the owner or the keeper of the cafe, who have been working there since the 70s, they say that these small changes for the better, the vents, etc., they have improved the conditions remarkably. Anything to add, Julia? So the third site or third case is not a museum, but this is a building that will be used both as apartments, and then there will be some kind of a shop or anyway a commercial premise. The Lydman House in Tammisaari. It's one of the oldest stone buildings in the town, which has mainly been a wooden town, very long. And it's located in I would say, the most important square there. It's opposite the town hall square. And you could say that it has been a rather prestigious building at the time when it was finished and designed by an architect. But it had some not so prestigious times after the Second World War, or in the 60s when it was converted into a department store, which meant that all the interior kind of walls were pulled down and the decorations from the facades were stripped down so that it would have a more modern look. The windows were changed, and then they would have also these big display windows and mechanical ventilation. And this actually needed a rather enlightened client who wanted to kind of, as much as possible, follow the original design of the building and give some of that kind of glamour back to this building. So you see here before and after. All this is designed by Juulia. So you got all these decorations, some paintings here, and the T-shaped windows, small windows, also the small bay window thing here. They have all been kind of redone. But also the natural ventilation was brought back. And this meant rather big measures, since the old stacks and flues, they were not really good enough anymore to be used. They had been kind of torn or broken, or they were in bad condition, so mostly they rebuilt the flues using the precast elements that both Leino and Juulia mentioned. And then also the chimneys were rebuilt. The apartments here, or the flats, will have natural ventilation, and also the commercial premises have natural ventilation. And what is more, when it does not have mechanical ventilation, the cold attic was retained, and also all the old structures, roof structures, that in themselves, I think, are valuable, and they have part of historic parts. And then this is my last picture to show you that even more modern buildings can still have natural ventilation. This is the so-called serpent house, käärmetalo, because it goes like this. Built in the early 50s and having natural ventilation. It was restored by the architect, restoration architect Mona Charlene a couple of years back, and they added some vents there to improve the ventilation. And of course there were other restoration measures done as well. Actually a rather big process, but so kind of well done, such a good result that it was given the is it biannual or annual Finlandia prize for the best architectural best architecture of the year or 2 years. Was it so? I don't remember really how often we have this in Finland. Is it every year? Yes. So it was kind of valued to be better than any new buildings, new architecture. This was regarded worth the prize. That's all I have to say. Any questions?
Okay, well, at the moment then we go ahead with Ülar's presentation, but thank you.
Thank you. En mä osannut istua siellä.
For some reason it says freeze.
Yeah, I freeze them for a moment.
Freeze? Freeze?
märkmetega versioonides. Nii et ära mängi.
Äkki sul saab läpakas panna veel vahel?
Saab ilma. See on mugavuse küsimus. See oli siis see.
Jah, selle on.
Hello.
Onks karva?
Jah, päeva pikk on. Pane endale kuskile, kui saad kraani külge või sinna.
Second try. So hello everyone here and in front of the screens. My name is Ülar Palmiste and I'm here presenting, sounds like a big thing, on behalf of Estonia, although I must say Estonia does not have like agreed, stance on this thing. So I'm also maybe let's show a little resume slide which mentions that why I'm talking here. I'm from Tallinn University of Technology. I'm a PhD student there for too long already, but I study somewhat related topic. It's airflows around buildings, more specifically how pollutants are moving around the different structures we have built, and I also work as a HVAC design engineer, so I could say I have like two views on this topic. So, but here's the disclaimer that this natural ventilation or mechanical ventilation, this is not like my, it's not my comfort zone. It's the first time I present on such a topic, because my main themes, I think I know the most about, are airflows and the indoor air quality. So that's the reason why my presentation is from those angles. It's probably a bit different from other people who might present instead of me. But here I am. So these are just some photos showing equipment to verify what is indoor air quality. So this is important. And there are different scales. You can see let's say, some defined spaces, but more about that in a minute. So I'll give a brief introduction. So I also, every year I give a lecture on indoor air quality in the university to future engineers. So, and I think this is a thing I should remind us why we ventilate. And also overview of ventilation types, which is more or less the same information we have seen from the previous presentation. But I think the way different terms are defined, this is really important to understand what I'm speaking about, because some words are, let's say, some phrases are different in my presentation, or the meaning is not the same compared to previous ones. So, and finally, I'll try to come up with a bit subjective Estonian perspective, because there, to the best of my knowledge, there's no like official one. Yeah, we'll get there. So, and also I asked a fellow engineer to send me some examples from maybe some older buildings that have some historic value. So for the introduction, I consulted with AI to draw two images using phrases: natural ventilation, mechanical ventilation, Estonia and Finland. So I think if you look if you pay too much attention to the details, you will see this is complete nonsense, but it has some entertainment value. There's another picture for the phrase natural ventilation versus mechanical ventilation, and obviously AI has opinion. This is the natural one and this is the mechanical ventilation. So, but in my opinion, it depicts quite well how some people, let's say, think about mechanical ventilation. I ask you to try to let go the semantics, like natural ventilation versus mechanical. This picture says it's like natural ventilation against unnatural, like some artificial, some, you know, bad thing. I think this, let's say, emotion might come just from the way we call those ventilation systems. You could call it this gravity ventilation and this is forced ventilation. There are some more neutral terms for those, let's say, systems. But okay, why we ventilate? Just a brief reminder. We all take, these are very rough numbers. These are not like exact things, but we take around 20,000 breaths per day. And let's put it into perspective. The mass we put through our bodies, it's around 1 to 2 kilograms of food. Maybe almost about the same amount of water. But when you consider all the breaths, how much air, mass of air goes through our bodies every day, it's a magnitude bigger than the, let's say, food or water we consume. So the quality of the mass we are, you know, letting through our lungs, it has a significant importance because there are research studies. It might be logical, but you must like prove even the logical things, because otherwise it's maybe hypothesis or speculation. So there have been studies where a large group of people were, let's say, it's not self-reported studies, like if I remember right, it was a more advanced study that people were like measured how long they spend their time in different spaces, and the conclusion is clear that we have become indoor species. Like around 85% of our breaths are taken in different indoor spaces. But for some reason, people think that yes, food quality is very important, water quality is important, but air quality, ventilation, let's get rid of this. This is just like this is just a waste of money. So this is a little bit about my research, like where is the air we breathe coming from if we mostly spend our time in those, you know, enclosed spaces. It's if you're in cities or, let's say, urban environments, it's not the air that's above the city which is, let's say, better quality. Actually, the air that enters the spaces come from the immediate vicinity, and it could bring in traffic pollutants, whatever. You know, there's too many to mention right now, but this is just like, maybe you could take a mental picture of the framework, that the air that's coming in from the outdoors, it's not automatically, let's say, fresh, because in English there's a phrase, let's bring fresh air indoors, but fresh actually might not be so fresh actually. So very important, the definitions, like these are the, let's say, the meaning of the words I'm using in this presentation. Ventilation is intentional process of introducing outdoor air. The word intentional is really important. We can have unintentional infiltration because the enclosure is not airtight. Actually, there is also exfiltration. If the pressure indoors is higher compared to outdoors, the air moves through the structure outside. So yes, ventilation, intentional process of taking air from the close vicinity and introducing into the spaces. So this is a slide from the lecture I'm giving in TalTech. It's in Estonian, but just to show that the air quality is not as easy because we just don't have the sensors to let's say verify the air quality compared to thermal comfort. So we have our indoor environmental quality, which can be defined through different measurable parameters. We have the outdoor space, that's from the last picture, the space surrounding the blue line. We have the ventilation. I haven't yet defined, is it natural or mechanical? It doesn't matter, it's just a way of the outdoor air to enter the building, and there always is a little infiltration. So I must sit down now. So there's ventilation taking the air out. There might be some exfiltration. So the air pollutants, there are emissions, not CO2, although yeah, people are emittents of CO2, but this is just indicator. This CO2 is not that like a harmful pollutant, but it is easy to measure it. Therefore, we can deduce from that let's say data how different pollutants that are more complicated to measure, how they behave in indoor spaces. There are different processes happening with those pollutants, and we could introduce some other, let's say, processes that influence the concentrations of those processes. This scheme was supposed to be quite complicated to convey the meaning that it's a complicated issue. Indoor air is complicated. So ventilation, when you think about the AI picture, like bad and good and bad, like natural, unnatural, I think of it, it's just the pressure difference. Is it natural in that sense? It uses gravity, or we use electricity to move the fan and create the pressure difference. So when you have natural ventilation, it's wind or buoyancy, the motors, natural motors driving the pressure difference. Mechanical ventilation, it's the fans. We use electricity, we move the fans, this moves the air. And also ventilation standards, or let's say an engineering approach also defines hybrid system, which is like combination. You could have one at some seasons and the other one at other, but this is mostly for, let's say, mild climates. I don't know any hybrid ventilation system in Estonia, because it's like hybrid cars. You basically have two systems, the mechanical and natural. It's even more equipment. So when we look natural ventilation, the wind-induced natural ventilation can be looked as single-sided. In Estonia, it's like ühepoolne. Basically, you open the window, the fresh air, outdoor air should come in through the same window and leave through the same window. Cross ventilation is läbiv õhuvahetus or läbiv ventilatsioon, where the air moves through the building. It doesn't require the stack effect, and this is probably also not for our climate. It's not very common because you just can't have the same wind conditions for every room. And then there's stack ventilation, which I think in Estonia, when people speak about natural ventilation, it's stack ventilation. You must have temperature difference when the volume of air heats up, it expands, it gets the density goes down, it moves up, and this creates the pressure difference, which is ventilation is always just pressure difference. Like you have the suction part at the lower building, so the air is coming to fill the gaps left by the rising molecules, and for that to happen, you basically temperature difference, and you must have some certain vertical path where the pressure could develop. But this is my subjective, let's say, opinion, or how I kind of feel how some people in Estonia think about natural ventilation. Let's say when I do renovation projects, then sometimes customers want some governmental grants, but they say let's do natural ventilation, but they mean let's do nothing. But this is not natural ventilation. This is no ventilation. So there's a difference, and this interesting looking building actually is a new university building in the University of Cambridge, which is completely naturally ventilated. But this is just to show that when you really design natural ventilation to fulfill indoor environmental requirements, it's not that you don't use equipment, you just use more materials, different methods, and there it might be even more. Yes, if someone wants to look up University of Cambridge, and this is a building where I gave a presentation there, and I know the, let's say, professor who did some of the calculations. This is, I would say, a rare example where I really feel this is like a modern example of natural ventilation. But as you can see, this probably cannot be, I don't see it as a mainstream solution, because if you want to make a new public or huge building, the natural ventilation must be in the driver's seat. It influences all the room sizes, heights. When engineers cannot like design it, it should be, I see natural ventilation more like a part of architecture, because when engineers get the drawings, I don't see it's possible to even do it on paper. So, and mechanical ventilation, basically three types. You either supply with fans, you exhaust with fans, or you have balanced ventilation. And with balanced ventilation, here you can have heat recovery. Yeah, I for some reason I assume people kind of know what mechanical ventilation is. So if you have any questions, you can ask later, and you can ask in Estonian. So as the focus should be on like natural versus mechanical, I don't stop here. I go to now I start like the steps why Estonian, let's say, stance on mechanical ventilation system is, let's say, preferred compared to natural ventilation. So the first thing is ventilation is not objective. Indoor environmental quality is the objective. Indoor environmental quality can be defined through some specific measurable, quantified parameters, and the numbers are in, let's say, regulation documents or standards, and where the numbers came to the standards, it's from the research, like maybe public health research or some, let's say, different type of research to give quantitative values. So when you have a building, you can go with some equipment and really verify is the indoor environmental as it should be. The European standard separates the indoor environmental quality into, I think, 4 classes. You can have like class first, or I'm not sure how it's in esimese sisekliimaklass, teine in Estonian, basically. I think most of the new buildings should go for, or should aim the 2nd class, and renovated, I think it's 3rd. I'm not sure. This is not my main thing, but basically that's the important principle, that indoor environmental is the objective. Ventilation is just a tool to ensure from this list of quantifiable things, the first. Ventilation is for indoor air quality. Just for the information, thermal comfort means temperatures, humidities, the speed, how fast the air moves in a room. This is everything under thermal comfort. And sound or noise and lighting. Again, this is another principle which is, let's say, my subjective opinion, how Estonian regulations define ventilation. This is not energy efficiency measure, just this is a tool to ensure the quality of air, just as we have food quality standards, water quality. These are also not like to save money or something like that. And a third thing, those parameters that can be classified under those should be continuously controlled during occupancy. It's not like let's have water quality 75% of time, or let's say 90% of time we have our food, let's say food quality, whatever you meant. So it's the same for air quality. So this is, let's say, those files in total probably around 1,000 pages is the basis for what's written to the regulations. I think it's already like 15 years ago. Different types of apartment buildings were studied thoroughly from building science viewpoint, from I think construction, like everything. It's like those reports are like at least 200 or 300 pages, and also in those research projects the air quality was measured in existing buildings, and first there are different, like some buildings were made of brick, prefabricated Soviet time panel buildings, wooden apartment buildings, and the common denominator was that the natural ventilation rates were not meant. The best natural ventilation rate, I think, was the worst for mechanical systems. So, and when I refer to the previous slide that air quality is the objective, we have some values from research, and the aim is to meet those values, because air quality is not just CO2, it's much more that might be happening, and research shows that some airflow rates is like it's not like optimum, it's the minimum, like minimum airflow rate. So from this research, Dr. Ülar Mikkola was, let's say, this is his thesis that's openly available from the university library, even the PDF, like summarizes this everything. You can see the quantitative measurements, like graphs, what's the situation with natural, mechanical exhaust. Yeah, and based on these results, let's say those values ended up in the documents that say when you want to get government grants for renovation, you must fill those indoor environmental quality goals. If you use your own money, do whatever you want, but this set, let's say, the ventilation requirements basically, and there were different phases. At first there was like first round of those grants, and after that there was another study like how those new buildings perform, and actually it wasn't that good at all. And from the second round of, let's say, the practical knowledge was already also taken into account when redefining the requirements, and this is the current state. I don't know how to translate the words from Estonian to English. I mean, I think Estonians probably know what the regulations are, but just I remind myself what I wrote here. So yeah, we have a government regulation that says in living spaces you must have ventilation, either natural or mechanical. Then there's another regulation I have a dedicated slide for that. And then this is like a regulation that defines the technical parameters that have to be met when you renovate using the, let's say, government grants. So this is in Estonian, yes, but it says, just to compare with your presentation, like how it's defined. Let's say you cannot find the word natural ventilation here, but indirectly, theoretically, you might think that natural ventilation might be here, although I don't believe that the way Estonian, let's say, energy efficiency different regulations have been set up.
May I interrupt from the article number 13? From which regulation is it?
In Estonia it's hoonete energiatõhususe miinimumnõuded.
Okay, it's linked in the ehitusseadustik.
See on omad määrus.
Jah.
On see sealt lingitud ehitusseadustik?
Sorry, ei oska öelda. Jah, when let's say, as a system designer, I list some normative documents in the projects, and this is one that should be, I mean, it doesn't have any like quantitative values to follow, but it says that the idea is mostly it should be heat recovery, mechanical ventilation, some exceptions, maybe you don't have to use it when the designed duration of if it works less than 4 hours a day. So there are also European standards that have been implemented in Estonia, and I look through how they mention different ventilation types. They mention natural, mechanical, and hybrid, and it doesn't differentiate, like you must fulfill the requirement for air flow rates in every system. And just there's lots of information, just maybe it's in liters per second. If someone is somewhat if someone knows about ventilation, then you can, see actually these are higher ventilation rates compared to what's usually, I think, used in Estonia. Another standard, this is about ventilation in non-residential. The beginning is the same, it mentions all different, let's say, ventilation system configurations. But hybrid, yeah, it's for me it's a bit complicated how to define hybrid ventilation. Like, is it like when you have natural on one floor, mechanical on the other? Is it hybrid? But this standard says that they cannot function at the same time. So the idea is that yeah, it's either one or the other. And you must be control how air flows. And it says the mechanical ventilation should be the go-to solution, and natural ventilation as exception can be used in unconditioned rooms or simpler buildings when you demonstrate. Like, I'm not sure what's meant by demonstration, like probably some energy calculations. I haven't never done that, I don't know, but it's this is in the standard. Also, there are so many buildings like residential, non-residential, new, old, very old, and there are those buildings that are old and have some historic and cultural value. For those buildings, the requirements are different. They don't have to fulfill the energy efficiency. They don't have to receive some energy label. But still there are like special conditions when you start designing such projects. You must, you have like a guidance what you can do with ventilation. But from my colleague who has been, who has more experience with such projects, he said that although there are no energy efficiency requirements, the owners, in his experience, prefer heat recovery mechanical because overall it's cheaper. And some references from my colleagues' let's say portfolio. The idea is that those buildings might have had different use historically, but now they are often public spaces, and for public spaces you have those let's say requirements that you should be able to verify. And sometimes if you have art or some artifacts that require a controlled environment, then there's no other chance. What else? Okay, this is one example where natural ventilation was maintained just because you could not practically build a mechanical system into those, let's say, very valuable halls of the Academy of Sciences. And I think the two first floors are naturally ventilated, and the supply air comes through, not through the openings, but ma räägin eesti keeles, sest ma ei oska inglise keeles seda öelda, et akende tihendid eemaldati lihtsalt läbi selle kuidagi, et kuna see visual aspect of the windows was also important, so that's the way they, intentionally introduced the leak, designed leak. Another very, let's say, prevalent type of old building that have cultural value, originally one family house. Now they're restaurants, schools, spas, completely different use case. And if you want to have a public space with these use cases, you must ensure the indoor and environmental quality requirements. That's the reason everywhere mechanical ventilation, or depending on the special requirements, maybe it's not, it might be like mechanical exhaust, not always like balanced ventilation. So, the conclusion based on the extensive research studies done 15 years ago, where we measured the natural ventilation, and it did not perform as well as the modern, let's say, levels should be. That's the reason why the regulations can't recommend natural ventilation as go-to solution, because there are no working examples that could be like successful case studies or something like that. I know that the natural ventilation is much more widespread in mild climates because you don't have to heat the air. I mentioned Cambridge University, but currently, as long as there's no heat recovery, it's really, let's say, complicated to fulfill the requirements using this system. Because everything should be commissioned, like verify the airflow rates. Is it so or not? So these are the main things that we see as a problem. And from my perspective, let's say I have lived in buildings with natural ventilation and mechanical, and I belong to the group that prefers mechanical because I feel like throughout the year the air is fresh. When I was living in my building with a stove in winter, when I opened the window, the cold air just introduced those cold drafts, and rather I closed the window, and when I measured the CO2 rates or knowing the new parameters, I see personally that the go-to solution should be heat recovery mechanical ventilation, because it's not dependent on the outdoor climate. You can control the parameters. But yeah, this definitely remains the, let's say, a hot topic, a hot debate topic, and I don't see it, end very soon, because the natural ventilation does work in some climates to some extent, and this is being tried to import it into our climate, but I won't say that I don't see it can't work, but I don't know how it should be designed, knowing I've done the simulations, dynamic simulations, not analytical with equations. I've measured, done some smoke tests around buildings. It's so dynamic situation, like how can you design a natural ventilation? This is like a science project to me. Oh, maybe not for residential, but my meaning for bigger buildings. But yeah, that's let's say that's how I feel. Maybe some people are not that pessimistic, but yeah, it will stay. We could make a series on this topic and focus on some even special aspects, like. If you have any questions, you can ask in English, in Estonian, and I have some questions wrote down to the previous presenters just to kind of get some technical idea about some things. So maybe ask me first.
Yeah, I'm wondering also, like you showed quite a big list of the studies, and one question that comes to mind is in those studies, what was their definition of the natural ventilation? And of course, like for example, if you would include naturally ventilated systems which actually only have window ventilation, for example, which are not complete systems for natural ventilation, then that would of course show quite bad results. Like for example in Julia's presentation, where we had the development of natural ventilation through the years, there's actually in Finland only one time period where they actually designed, in the old days, where they designed like the system so that it actually gives a good air quality. And now we have returned back to that. We are using about the same kind of like design principles now in the new systems. Because of the new regulation, but then there's many ways that there's many types of systems that you could call natural ventilation. They would get bad results, but it's not really.
Yeah, in those buildings, it wasn't very clearly defined that natural ventilation is, but the system was that the leak was coming through the windows. Because the windows were bad during Soviet times. There were no holes, but after the first round of if I remember right, around 2014, government issued grants based on the studies, and you could renovate using natural ventilation, if I remember right, or was it mechanical exhaust? But after that, they introduced those like holes, but it's still, let's say in Estonia, the good building practice is to follow the standards or regulations, and if they have a number that indoor air quality class 2 or 3 has this air exchange rate, and if you measure it, and instead of exchanging the air in 2 hours, it's in 4 hours, like you have a volume of air and it's changed in 4 hours, that this was just low, and that way, that's the reason why it said it's not working. Although I know, yeah, from the fluid dynamic perspective, the system might work for the first floors because you have higher stack height. But if you have an apartment building 5 floors, the stack height for the last floor is so short. Actually, it might be that sometimes the airflow is the other way, because modern buildings have kitchen hoods. And you said that the pressure difference in summer is 2 to 5 pascals, and in winter 20 pascals. But my gut feeling says when you run the hood, it just brings the air back down. So I don't know how is the compensation of kitchen hood solved in natural ventilation, because it's like a magnitude of different like pressures.
Yeah.
Mm-hmm.
Has anybody studied the effect of wind cowls? Because they really make a difference when you have a situation like that you're on the upmost floor and the flue is too short, actually. But with the spinning factory, you can guarantee certain kind of ventilation rates.
Is it a thing that was historically present in your buildings, or is it like a new thing, the cowls? Because both.
They have been used traditionally, and now they are sold again.
I think in Estonia they have not been traditionally used. Maybe I'm wrong, I don't know, but I know there's a professor in our university, Kimmo Lyllykangas, who actually has done some experiments with those cowls. I don't remember the exact results, but there was that assumed performance was very different from the real. But I don't remember what was it about. But yeah, there was a master student. There's even a thesis that's also publicly available on our university site, studying those wind cowls. And I've been to. It was a University of Newcastle, another professor. Studying also not wind catcher is a bit different thing.
If I remember correctly, the student you are referring to, the houses that he was studying were the kinds that didn't have a proper natural ventilation system, and he chose those because there was enough material easily available, not because they would be the best possible natural ventilation systems. And if you don't have enough fresh air coming in, then of course the twisting rotaries won't help that much. Or if you don't have enough flues, then you can't repair that so easily.
I feel like that might be part of the root of the entire question in Estonia, because in those studies that you mentioned, need korterelamu, telliskorterelamu uuringud, was the condition of the natural ventilation system evaluated at all? What was the condition of the vertical flues or the openings in the walls? Was that even?
Yeah, this was looked at. You can see there. I remember some pictures like taken of them. They were very bad, in very bad shape. When the natural ventilation, at some cases, at higher floors starts working vice versa, like it sucks the odors from other apartments. So this is just about the, let's say, the state of material or construction was bad. It doesn't mean that, it doesn't say that natural ventilation is bad, but the state is bad. But still, if you have flat roof and higher floors, even if you calculate, I don't see there's enough pressure difference to be like sustainable. When you turn on your kitchen hood, it sucks out like at least 25 liters per second. But the overall airflow rate for 1 room or 2 room apartments is 15 to 20 liters. So the air must come from somewhere. And if you don't have the pressure difference through stacks, it's very, it might just suck the air from, whatever. So I see this, this is one question, how you show the picture of a new apartment building, but do you know how it's solved in this building? Because when you have a airtight building, you really must intentionally introduce the compensation air. Yeah, so this is very interesting to me.
It has to come like at the proper pressure level. So basically, I have one apartment house that I was designing the natural ventilation in, and they did it like this. They wanted to have the mechanical exhaust for the kitchens, even though it can be done with a kind of like a circulation through a filter, but they wanted to have the mechanical exhaust outside in the kitchen. And they did it so that they had a specific, they had a specific vent that you open then that is big enough for to bring in the enough fresh air to compensate for the use of the exhaust of the kitchen.
Okay.
And the same applies for fireplaces, for example.
Right.
Many times, like the fireplace suction creates this situation from another flue. Yet the flow is reversed because we would use the fireplace. The same principle you have to apply, that you have to have enough fresh air coming from a big enough vent to compensate.
I've done an experiment where we had a kitchen hood, fireplace, and very airtight building, and we made the fire and then just turned on the kitchen hood and made it to 100% capacity, and it like in 2 seconds the house was full of smoke. Like it's like instantly like so yeah, compensation. Yeah.
Do you want to answer?
I was thinking when I was hearing Leino's answer that actually there is a simpler way, because normally when you have a fire in the fireplace, or if you have the cooker hood fan working, then you are present at the house, then you can just open a window. It's a cheaper way. Of course, it's not maybe as controlled as when you have a special vent, but that's how old houses work.
That's the thing I brought into my design project reports. When I see that there's a fireplace and ventilation definitely is not enough, or there are those cases, then I see it's a very serious issue, and this is, you really must open the window. Otherwise, there are accidents sometimes when the gas burners, or go out and you have this carbon monoxide, and this might be a really serious issue if the pressure is in a wrong direction. And yeah, I have a question. Are those finished results somehow published or like studied in similar sense that people going in with some equipment to verify airflow rates or something, or how do you even commission those? Like, don't you have like requirements, like when you finish the system, and there should be the protocol how it works? Because this is a question mark to me, how it works in like modern times for new buildings.
The requirements for the air exchange rate are the same, like I had in my presentation. This mechanical natural is the same requirement, and they will in principle at least, and in this apartment house that we did, they do the measurements as normal, like they do go in and measure all the airflows in all the vents. So, and that was, there was no problem because the design has to be, of course, the design has to be proper so that there is enough of those ducts and vents. If that's not the case, then of course it cannot work. But maybe the big issue nowadays, also in Finland, is that this is not taught in the schools, and there are no building design programs for this purpose. So it is up for the designer to study and to make the tools for the design of it. So it goes wrong easily in that part if the designer is not educated enough in this subject. It is a different subject than the mechanical ventilation, and there you have all the tools in your programs. You have all the tools for it, so it is easy for the designer, not so easy for a natural ventilation designer. So if the design is not done properly, then you will have problems, and they come up in the measurements then. So that's it has to be well designed to have good results.
Do you have like idea when you have like a, let's say, new apartment building, like maybe this the one they are building right now, and in winter you have lower flow rates, and you present it as it could be a good thing, but let's not focus on the air quality, but on humidity. Like in modern buildings, there are lots of sources of moisture. Like are the flow rates maybe too low, or because this is another thing. If you have moisture, you could have really bad problems. I know the fellow engineer mentioned. Okay, this was an old, maybe medieval building in downtown Tallinn, where there was, I think, new apartments, but natural ventilation, but it got mold because the airflow rate was too low to try let's say, to safe levels. So I'm thinking in winter, when you try your clothes indoors, you go to shower, the exhaust rate from wet rooms, like.
As I said, the airflow rate requirements and the design airflow rates are the same for mechanical and natural ventilation. There is no difference there for the capacity, and in the winter time, if you open the vents for the natural ventilation, you will have many times the requirement airflow rate. Also in the winter time, in the summertime, the moisture is more of a problem, and then you are reliant on enough capacity in the system. So if you open your vents, you will have enough flow. In the winter time, it's the opposite problem, that the air might be too dry for comfortable and healthy air quality. That if the air is changing too much, and then you have to have proper adjustment possibilities, so that you can also, in the natural ventilation, you can close the vents enough so that you will not have too much airflow. But if it's properly designed, then too low airflow rates won't be a problem.
Okay, the same actually is recommendation for mechanical ventilation. When it's very cold, you just lower the airflow rates. But
yeah, you can do that.
Yeah.
One thing that affects the indoor quality is also the materials of the house. And if you want to build a house with natural ventilation, I always suggest that you should be using materials like hygroscopic materials that can take moisture when there is a lot of it, and then give it back when it's too dry. And that would lessen the need for air rates. But I've been living in naturally ventilated houses, like 100-year-old houses, all my life. And nowadays, of course, all the houses, like the old houses in Helsinki, are painted from the inside all over with plastic paint. And that's not a good thing, because then the structures that could dynamically buffer the humidity, they can't do that. But still, most of those houses were really fine. Even if there is this plastic paint that sort of forms a plastic bag, which is not idealistic at all. So, because of my experience, I'm not really worried about. Of course, there needs to be understanding of the system, and an easy way how a housing company can help this is once a year make make recommendations for the occupants how they should use the system, and once a year put it in the post box of every apartment. It's really cheap, and even if the occupants move away and new ones come in, then they soon will get the introduction to natural ventilation. And to help this situation, we have this heritage agencies thing in the internet that I was showing, where you can find these. I suppose it's possible to copy text there and then translate it with people, so it could probably be used in Estonian as well. So that's like a practical answer to the thing, if the occupants know enough of natural ventilation. And it's much cheaper than starting to build a mechanical system on an old house.
Any more questions?
I have one. Just about this house in the downtown you mentioned, that there was more than everything. Do you know this natural ventilation, was it thought through, or this was like you at the beginning said, Estonian natural ventilation means no ventilation?
I can't answer to it because I don't know the details. I just remember on the spot that it was mentioned. I didn't add it to the slides because I'm not sure if, because let's say 100 years ago the indoor environmental quality or what it was so different. There were no such requirements in Estonia. When you look at Britain, you can already see the ventilation rates or some values that were thought of, like what it should be. For example, in Britain, I think it was like 25 liters a second per person. We were here speaking about like 5 or something, but now modern research also shows when you consider the viruses and stuff like that kind of pollutants, then you really need 25 liters, because the lower rates are based on odors and just to dilute it enough so you don't distinguish it. But actually health-based guidelines in recent research papers propose that it should be even higher, but yes, of course, it takes some energy, it costs, but if you agree that indoor environmental quality is the objective, ventilation is not the energy efficiency measure, and when you want to fulfill those numbers, I think it's really important in public buildings, schools, where people, a lot of people are together, and because there you can really show that there are fewer sick days, stuff like that. There are research for that when you play with those ventilation rates. Yes.
I'm going back to this old house that you were not quite sure of the system. If it was from Middle Ages, it originally had fireplace heating that would have exchanged the air very efficiently during winter. And nowadays it's probably central heated. So there might not be enough flues. And if you don't know if there was a replacement air system, we cannot really decide because of this house whether natural ventilation is good or not.
Yeah, I think my gut feeling is that they just probably wanted to save money. Let's do natural ventilation without thinking about through where the air moves, how to achieve the pressure differences, yeah.
I think it would be interesting to see whether the studies that have been conducted, would study natural ventilation and building in Estonia, whether these ventilation systems were first designed in a proper way, were they maintained when they were studied, and did the occupants and even researchers know how to function them, how to properly use them to objectively more or less say that whether the system works or not. Because most natural ventilation systems that I've seen in Estonia, they are of the worser kind that Julia showed, that with the overflow effect, with stacks only in bathrooms and kitchens. So it's not a very efficient natural ventilation method, first. Second, do occupants know how to use it? And do they even block those channels intentionally sometimes to stop heat from escaping, perhaps? And and whether the occupants even know how to maintain them, have the channels become blocked, or I think that is an aspect that might not have been studied in those earlier studies. Or what do you think?
I can't say for sure because I didn't look this aspect from the studies, but I think the general idea was that the walls, the windows are not airtight. It's enough for the leakages, and I think for that was the design basically. Just a stack, just higher levels. Floors had lower stack height, so less pressure difference to drive the ventilation. So it depends if you are living on the first floor or the fifth floor. So I think that's the original.
But I'm just wondering whether that's an assumption of the researcher, or was it what actually the architect designed, and whether perhaps if it was designed, the construction people or the owner simply decided that let's cut corners, let's not build these channels or save money, etc. So I'm just
it was
wondering
Soviet times, everything was
or even
stolen.
earlier during the First Republic and the Russian Empire. That I'm just it's just an interesting thought to me. Do you have?
So just a curiosity question about air pollution from outdoors, and how much of it can be filtered out, and how does it affect the energy efficiency of the whole system?
Energy efficiency.
Let's start with the pollutants first.
Pollutants. It really depends where you live. Although, let's say, Estonia is considered like the best air quality in the world, like top 5 something. But reality is when you live in dense urban areas with traffic, when cars drive, there are like micro fragments from tires, for example, particulate matter, that are so small that when they enter the lungs, then they can stay there. And some fractions are even so, let's say, small that the nose cannot, catch it, and it could go to your lungs. So there are this is about particulate matter. Particulate matter could be, let's say, in Estonia, suburban areas with lots of private houses with fireplaces. When they burn wood, this introduces particulate matter into the air, and the measurements have shown that the contamination stays in those areas, and this is a health hazard. Let's say particulate matter is the worst one. This is established as let's say, this causes serious illnesses in long term. Not like air pollution is not acute usually, only carbon monoxide and stuff like that. How it can be filtered? Mechanical ventilation system has a section where you can enter a filter. I should have a picture because it's amazing how dirty it is in 4 months. There's a saying that if you don't ventilate or if you don't filter the air, your lungs will. So to some extent this is true, because if you live in an area where the outdoor air has some pollutants and they enter the space and you breathe them, then it could potentially have long-term effects. I think in natural ventilation and mechanical exhaust ventilation, mechanical exhaust is you have like a fan that sucks the air, and the air is introduced through vents. Some vents have a small filter, so the air coming into a room goes through a filter, but it means the user just have to replace the filters. This is like a regular maintenance, basically.
In natural ventilation, it's also possible to filter, but not with fine filters. And then you can take away from the fresh air, like the bigger, small particles and pollen, but not the finest small particles that are most harmful. But what happens when we use fine filtration, we also filtrate like bacteria, and then inside air becomes very different from outside air. And we have results already from studies from kindergartens where we have so-called like natural kindergartens where children are more out, they are less sick, like if they spend a lot of time outside digging dirt from the ground, they are healthier than if they are staying inside the building all day. And we know that these small particles are harmful, but there are like really strong suggestions that it's also harmful for people to live in like without getting the normal amount of bacteria, like having whatever things that are outside. And we know that at least in Finland has had like, I guess, at least as long as Estonia, like a very strong ventilation industry, and like we are really like technically orientated. And Finland has a lot of autoimmune diseases like allergies and asthma and things like that. And there are also studies about like on the Russian side of the border in Karelia, there are people that have like the same kind of genes as Finns, and they are a lot more healthier considering autoimmune diseases. And one big difference is that they don't have mechanical ventilation. There are of course many things, and it's impossible to say that if it's only this. But personally, I would rather breathe air that reminds of like outside air. Like I'm sort of old, and I was raised at a time when it was considered that outside air is more clear or pure or fresh than inside air. And somehow my feelings and my body, they tell me that if I'm enough outside, that's of course again like a complicated question. But I still sort of believe that inside air, if it doesn't have any special pollutants or something like a defect like that, inside air is not as good as outside air. Like in summertime, I like to sleep with my window open, and I'm not afraid that I live in the center of Helsinki, but in a good place, not too much traffic. Well, if there would be a lot of traffic, I would suggest that people would be using this kind of not so fine filters, because that would take like a lot away from these small particles.
For here, I must say I know some of the research, but I'm not sure if this is true. I must see the research papers, because I've seen the same argument for Great Britain. They insulated the houses, made them airtight, but did not work with ventilation, so the airflow rates went down, and the same results basically. And the filters, the fraction, I'm not sure how. I think the regular filters cannot catch the bacteria.
Fine filters can. They catch the bacteria. Like if the filter takes away the, I'm very bad with numbers, but I think it's like 2.5. That's one whatever.
Particulate matter, yes.
Yeah.
Uh-huh.
If you can take that away, you take away the bacteria as well.
Okay, I must look into it, because I know the phrase is building microbiome, like the tiny creatures living but
we have some studies I can find if you're interested in.
Yeah.
They're done in Kuopio University.
Mm-hmm.
They were studying like a small, like a one-family house area, and houses with natural ventilation and mechanical ventilation, and these small particles. And it was showing that small particles are not healthy, but I think it was also showing that if there is certain amount of small particles outside, then in a natural ventilated house, in the inside of the house, it's like half the amount what's on the outside. So if you don't think that it's unhealthy to go out into your garden, then you shouldn't be worried about if you're getting like half of the amount of small particles in the house, I think. But I'm not a doctor, so I really shouldn't be talking about this.
Yeah, the global average is that the indoor concentrations are 3 to 5 times higher than outdoors. So my knowledge is that if you lower the rates, this makes it worse. If you move more air, this makes it closer to the outdoors because it dilutes the pollution or takes it. But filters and bacteria, this is, I must look into it because, yeah, let's say this is news to me because I've heard the argument, but for the cases where the building is airtight and you don't ventilate right, like that's the phrase in English. And of course, this is complicated issue. It's not only particulate, there are gases. You can introduce particulate matter when you cook and you don't have hood or you don't turn it on. We have made some research that when you measure the concentration, it's higher than in Beijing when you have those, you know, crazy pictures. So, and this is not outdoors. This is everything we do indoors. So there are so many, you know, potential emission sources that are different from, you know, 50 years ago. Like just modern living introduces something. Okay, I'm not sure what's the clock like.
Just stop breathing. Kas on veel küsimusi? Do we have any more questions?
Yeah, one more.
Yeah.
To the Finnish colleagues. I don't know, I didn't read the book, but maybe the info are there. But do you have principles how the solution for the natural ventilation should be? How big the holes in the wet rooms, in the living rooms, how much corner then can be, or so on?
Yes, one flue for every room, for every bathroom, every toilet room, and then one inlet for every living room, not in the sense that there is a bedroom and a living room, but like all proper rooms need an inlet. And then what would you, Leino, suggest about the height of the flues? If it's less than 4 meters, then I would suggest that you use wind cows as well to make sure that there is enough air going through.
Okay, is there a principle the hole in the wet room should be twice the size than for the living room? Or
not in apartments. It's like half a tile, like 13 to 15 by 13 to 15 centimeters.
Okay.
Oh, Leino, what would you say?
What did you say?
Like 13 by 13 or 15 by 15 centimeters?
Yeah, 15 by 15 centimeters.
And if you're using
the old tile
yeah.
rooms, that was the size, and it works quite well.
And the same in the wet rooms and the living room?
Yes, because the wet rooms are normally smaller rooms. Then of course if you have a huge bathroom, depending on if you have like 4 showers there, then maybe you need more. But if you have 1 shower and the use is like normal family use, then maybe I think this 1 flue is enough. And then, of course, the occupant must realize that there is a natural ventilation system, and if there is like extra use of water, then the door of the bathroom should be left open after using it. So it's, to me, knowing these things, it's very simple, very practical. But of course, if the occupant doesn't realize that it's not a modern, mechanically ventilated apartment, then they should be advised.
Okay, thank you.
Okay, but I think then it's time to start wrapping up. Thank you to Ülar. And I think I will now transition back to Estonian, as most of the content has been discussed now. All of our presentations and will also be available on our website along with recordings of the presentations. Et eesti keele peale minnes, et veel kord, kes on meil ruumis, et oleks tore, kui annaksite ka meile tagasiside lehega, et vaadake, et olete registreerimislehel. Ja kui teid huvitavad ka täiendõppepunktid, siis pöörduge Elo Lutsepa poole, seisab taga. Ja ootame teid ka meie maikuisele seminarile, kus tulevad siis teemaks ajaloolised detailid, nii kivi kui ka puit ajaloolistel hoonetel. Aitäh!